here we go. So we're gonna keep practicing arc length and surface area. Before we do, let's just recap. We were a little bit rushed at the end last time. So let's just recap what we did. We said that we thought that maybe that the rate of change, we conjectured that the rate of change of surface area, big S, was possibly 2 pi r. And so then we said, okay, maybe our surface area function, say from a to x, is integral from a to x, 2 pi r, whatever the radius is, we have to figure that out, dx. But we did the example with the sphere, and we found out that, hey, no, something's wrong. This was way too low. We got way too low of a surface area. And that's because we were what? We were summing up the 2 pi r's as that was generated, as those ribbons were generated parallel to the x-axis. And we said that generation of those ribbons doesn't match the curve. And so we got this kind of stair-stepping effect, which even when the intervals get really, really small, it still doesn't give us the right surface area. So what was our remedy to that? We needed
frustums.
Yeah, we call them frustums. We needed these same ribbons, but not according to this dx, but according to ds, right? So this was dx. We needed to expand, have 2 pi r, the circumference, generating surface area, but along like a slanted edge. And that was our ds from when we did arc length. So rather than have dx, instead, to get this correct, so this is not right, instead of dx, we want ds. So really what we want is 2 pi r ds. And we know what ds was from arc length. It was square root of 1 plus our function value squared dx. So this whole thing was our ds. So therefore, our rate of change for surface area was this whole thing.
I'm sorry, does that say f prime?
Yeah.
Okay, thanks.
So the rate of change of surface area is not just 2 pi r, which would assume kind of horizontal generation of the ribbons, but it's 2 pi r 2 pi r times the square root, which is like a transformation from horizontal generation of the ribbons to the ds according to the arc length generation of the ribbons. Those were what? Those were like the little tangent segments, tangent to the curve at the beginning of the interval, right? So we took a segment, we took the beginning of the interval, we got the rate of change of the function, and we generated a tangent segment. So if our ribbons generate that way along that line, then we get the right surface area rate of change.
So we're replacing dx with ds,
That's
right?
right. Which
and
is
then we put the square root in. But then why do we have to add in a dx if that's what we had already replaced it with?
ds is this times dx. That's what ds is. ds is the square root times dx.
Right. Okay, sorry.
Yeah, it's okay. No problem. So this is our ds, and then that makes all of this the rate of change of surface area with respect to x. So all this, the 2 pi r with the square root, makes the rate of change of surface area with respect to x.
So this is when we
Nice. Again?
Wait, how come we're not using for t for this one? For like.
Oh, we should have. Yeah, this should be t. Thank you. It should be t. These should be t's.
And the square root is just like, that's what the arc length is? That's the rate of change of the arc length?
Yep. The rate of change of arc length was the square root function.
Okay, and we're just really combining these two ideas.
Yep, kind of. Yeah, we need the rate of change of arc length so that these ribbons grow according to that the 2 pi r sweeps out area according to the arc length function rather than just x.
Okay, thank you.
Sure. Okay, is that clear? All right, so we're going to practice. We're going to practice all this stuff, and we're also going to be using GC to help us understand stuff. So I have a nice activity here. So first of all, so the first thing is I got this function, and notice that I've used y as the independent variable. GC doesn't care about that. That's just like a place filler. Like if I put x or t or a, it would be the same thing to GC. But I'm putting that in there because I am truly wanting to think of my independent variable as a y coordinate. So this is different than what you're used to. In your whole math career, the convention was put the independent variable on the x-axis, okay? And then let your dependent variable be values of y. So now we're going to change it up. So that's just convention. There's nothing intrinsic about the x-axis that it should be independent, and the vertical axis it should be dependent. It's just the way we've always done it. So if we're smart, we should be able to switch it up and make sense of it, right? So what we're going to do is we're going to graph g for the independent value being y. So we're going to put the independent value y on the vertical axis. So we're going to start here. We're going to think of values of y and then corresponding values of the function being on the horizontal axis. So how will I tell GC to graph that? What should I do to tell GC to graph this function g so that y values are my independent variable? What will I type in now?
X equals gy.
He wants x equal g of y. What do you think? So now these x's and y's are talking about telling GC about the graph. So what we're telling GC is take y values on the graph and substitute them in here. And whatever you get for that, those output values, graph those on the x-axis. Graph those according to the x-axis. Okay? And so let's do that. And it says we're going to graph it from 1 to 4. So what goes from 1 to 4? X or y? Y. So let's see how we did. Okay? So here's that graph. And so now we've got to kind of work hard here to make sense of this graph. So let's pick a point. And so here's the point, say, (1.17). X is 1.17 and y is 3.23. So I'm seeing that. So if you click on the graph, you get crosshairs, and wherever the crosshairs are, you get the coordinates there. 1.17 about and 3.23. So what's the meaning of that point? What's the meaning of this ordered pair? Given a value of 1.17, the value of the function is 3.23. Is that right?
That would be in terms of x, right?
3.23 should be the surface area given at 1.17.
Okay, we got a surface area function here. Is this y value the surface area?
For every value of y, 1.17 is the natural log of y.
For every value of y?
Just for 3
For the value of y.
Yeah, right. So our input is, so we start here. Input is 3.23. So given an input value of 3.23, now we're showing it on the y-axis. The resulting value of g of y, is shown on the x-axis. So this is g of y, or 1.17, meaning that the natural log of 3.23 is 1.17. So this is y first now, instead of x first, y first. And then this point tells us for that value of y, the corresponding value of g of y is 1.17. And that's shown as the x-coordinate, distance from the y-axis this way. Okay, does that make sense? Any questions on that? So this is reverse of what you've been trained in your whole math career. But if we really understand graphs well, we understand functions well, we should be able to make sense of this and see it that way. It's good practice for our understanding. Okay. So now I want to define the arc length function for g in terms of y. So now again, my independent variable being y, and I want an arc length function. And so let's write that out, and then I'll reveal it. I think I've already got it in there. So we are going to use s of, right, little s, and we're going to use our two argument notation, a, and what's going to be our independent variable?
Y.
Y now, okay, and that's going to be the integral from
Y.
a to y of what? What's our rate of change of arc length? Rate of change of arc length. Square root of 1 plus
G prime to y, and then square of that.
Yep. So it's going to be the derivative of g with respect to y, and we need to square that. But we need
T.
Yeah. So this is a y coordinate, but we need something different, right? We use t to represent every y starting from a until y, and then we need dt. What do you think? All right, and so I think I called it s sub g. So let's see if that's the same thing we just wrote out. Is that the same thing we just wrote out? So I'm saying this is the arc length function for the function g, starting from a to y, integral a to y, 1 plus derivative of g squared with t's in there, dt. Okay, so that's what we did. And so now I want to graph the arc length function, right? So I want a function that gives me how much arc length for any value of y, right? But I want to do this in the conventional way. I want to put my independent variable on the horizontal axis, and I want to put my arc length on the vertical axis. So this one was unconventional, but when I graph the arc length function, I want to do it conventionally. So how do I set that up in GC? So what am I going to write in GC? So first of all, is it going to be, so values of S of G are arc length. Do I want to make those Y values or X values?
Why?
Yeah, so now I'm doing this in the conventional way. I want the output of my arc length function to be on the vertical axis. So I'm going to set y equal to values of S of G. Okay? And now, so now I've got I did the two argument notation. So what am I going to put for my arguments here? So I need an argument for what I called A back here, and I need an argument for Y. So what A, where are we thinking about starting accumulating arc length?
1 to 4.
Y equals 1. All right, so what do I want? 1 to 4? 1 comma 4?
Yeah.
So will that be a function? What will 1 comma 4 give me?
A value.
Yeah, that's just going to be the total arc length, right? It'll be like the accumulation of arc length from 1 ending at 4. But I want a function. I want to be able to crank out lots of values of arc length for any y value, right? For any y value.
1 to y.
So, but now I'm telling GC to graph it. So my independent variable y, this is telling GC to graph. Where do I want to put my y's?
Could you do e to the x?
No, I just want to tell GC to put the independent variable of this function, or the y values over here. I want to tell GC to put it on the horizontal axis. Does that make sense? So this is my graphing command. This is my graphing command. It wants to, if I want to tell it to graph something, GC is going to want to know, what do you want to put on the x-axis and what do you want to put on the y-axis, right? So what am I putting on the x-axis in this new graph?
Function of G.
Okay, what I'm putting on the x-axis in the news graph is what I was doing over here, y. The independent variable over here was y. And that is my second argument. So I'm telling GC, whatever's here, put it on the horizontal axis. Okay, but now I want to open it a new, so in order to open up a new graph, I can have two panes at once, two graph panes. We use apostrophe on the y's and x's. So make sure you don't confuse this with like prime for derivative. It has nothing to do with that. GC does not use apostrophe as derivative. So it uses it as telling GC, open up a second window pane for graphing. So that's what this is going to do. And then I want to do that from what? 1. So what do I want to go from 1 to 4 in the new graph? X or Y? X, right? So I took my arc length function, which had its independent variable y. I want to put that independent variable on the x-axis. And then I want values of the dependent variable, or values of arc length, to go on the y-axis. Does that make sense? So let's take a look. And so what will it look like? What will the arc length function look like? So before I turn that on, let's predict. So because I have the y prime and x prime in a command line, it's opening up this new window pane, but I haven't turned the graph on yet. So what will it look like? Where will it start? What will it do? Any ideas? At what point will it start?
0, 1, or 1, 0.
1, 0. Right, because my arc length for my independent variable over here is this value 1. So it's at y equals 1 and increasing from there that I start generating arc length. So over here, that independent variable is on the x-axis. So that's going to start generating arc length at 1. And then from 1, 0, where's it going to go? Up or down? Up. We know that the arc length and surface area are always increasing functions. You're always adding on stuff. You're never taking away stuff as you generate a curve or you generate a surface. You're going to always keep adding stuff on, so those accumulation functions will just always increase. So let's take a look. There it is. Okay. So let's interpret a point on that curve. So here's the point, 2.5, 1.77. What does that point mean? So what's the meaning of that point, which is 2.5, 1.77? Anyone want to give it a shot?
I'll give it a shot.
Sure, please.
So the independent variable x, when input to a function of s of g, at that, or when you put it into the function, it will output 1.77.
Okay, that's good. Can you interpret it in terms of our context, right, which is arc length? So what does all this mean in terms of arc length? But what you said was correct. We want to interpret it in terms of arc length.
At the point 2.5, the arc length of the function will be 1.77.
All right, and so what does that mean? At the point 2.5. So you mean this? At the point 2.5?
No, at the y value 2.5.
Right. So when we're at the y value over here of 2.5, so what is the 1.77?
So that it would be on the other graph 1.77 on the x out.
So this is to be 1.77. So when I'm 2.5 here, I'm 1.77 here. Is that right? So some.
It's the accumulated arc length.
So is this right? Is this picture that I've drawn correct for interpreting this point right here?
It doesn't look.
No.
So, right, because look, this is coming in at about, 1, somewhere close to 1. 1.77 is out here. So something's wrong. So
Is
what?
1.77 the accumulated arc length from y equals 1 to y equals 2.5?
Yeah, did you hear that? It was well said. So it's the accumulated arc length starting from here, because this function is giving us arc length along this curve. So when we reach y equals 2.5, we've accumulated 1.77. So what can I can draw on here? I can say, look, it's this length right here. That's my 1.77.
Sorry, could you repeat the last part where you said 1.7 is the accumulated arc length from what point?
Well, so where does our curve start? We're talking about our independent variable is y, right? So starting from where are we accumulating arc length? Y equals what?
1.
1, right? This is where we start accumulating arc length because there's no curve down here. So when y starts at 1, and y increases, we start accumulating arc length. When y reaches 2.5, how much accumulated arc length do we have?
1.77.
1.77. The length of that little curve that I've highlighted in black there is 1.77. That's exactly what this function is telling us. For any y value over here, the y values on this graph tell us how much arc length along the red curve. Does it make sense?
Yeah, thank you.
Very good. All right, so now I want to know what's the whole length of that red arc. So the red arc stops. How can I use this graph to figure out how long is that whole red arc? What should I do? How long is that piece of arc there, that curve, that red curve?
S of G from 1 to 4.
Right. So yeah, so I could use function notation. First of all, I could do S sub G of 1, 4. And it tells me that the whole arc length is 3.3428. How can I use the graph to answer that same question? So over here, how can I use the graph then to answer that same question?
Would you just move your cursor to the 4 point?
That's right. I'm going to move my crosshairs so that y equals 4. You hear a little knock. And lo and behold, what's the y value? That's our 3.428, right? So the y values on this graph are how much arc length you have on this one for any given value of y, or independent variable, going vertically. Okay, doesn't make sense.
Yeah.
Anybody have a question? So we're really challenging ourselves here, right? So this is good because we're challenging our convention, our norm about putting the independent variable on the x-axis, and then it exercises our understanding of graphs and understanding of functions. But does someone have a question?
So how does just changing what the independent variable is to x give us the arc length now?
Well, the function was the arc length function, right? Our S sub G was an arc length function. But it was how much arc length you have for values of y. For the current value of y, how much arc length you have starting from here.
Okay.
So that's why we get arc length, because we made an arc length function. But the difference was now that arc length function is a function of our y variable.
Okay, and then you switched it to the x.
Then I took, over here I graphed, okay, we're going to put those y values here. I'm going to put those y values down here. So we start at 1, and this is y increasing. These y values increasing. And then the y values on this graph then are giving how much arc length we've accumulated. as y increases this way.
All right. Okay, thank you.
Yeah, so it's good exercise for our brain, right? Other questions?
Just to clarify, Professor.
Yeah.
So the graph on the left, that is just the function g of y is the natural log of y.
Right.
And then the graph on the right, we first then did the arc length accumulation, and then we switched our variables to placeholder, like x was changed to y prime, and then y was changed to x prime, just to help us like understand it a little better, and then that outputs arc length, the accumulation of arc length.
Right. So down here, these values, the meaning of these values on my horizontal axis are the y values over here, the input, the independent variable. And then the meaning of these y values on this graph are how much arc length we accumulated on this graph. That's what I did. I said y on the right is the arc length function starting at 1. And we're going to put the independent variable, which was y over here, we're going to put that on the x-axis. Okay, sure. All right, so let's move on here. Okay, we already did all that. Okay, so surface area. So now I'm going to rotate this curve about the x-axis. Let's make this a little smaller here. And I'm going to keep my y as the independent variable. So what will this look like when we rotate it around the x-axis? What kind of thing will we get?
It'll look like a sideways funnel.
Yeah, like a funnel kind of shape, or like a horn on the bell on a brass instrument, right? Just if you cut the bell off of a trumpet or a trombone, if you just sliced it off and just took the end of it, something like that. Okay, and so now we want to generate surface area. And now we want the rate of change of surface area, right? So here's the key with coming up. So the rate of change of surface area in general generically is 2 pi r times the square root of 1 plus your function value derivative squared, right? So that's our generic form for the rate of change of surface area. So really the biggest challenge to this is determining r. What is r? Okay, r is the radius of our frustum, which I'm calling ribbons. Okay, so r is the radius of a frustum or ribbon. And so the best way to get this radius right, to get it correct, so you can get your rate of change function right, is to make a picture, draw a picture of a typical ribbon in some typical interval of your independent variable. Okay? So in my experience helping students with these surface area problems is they never draw these pictures. They're just trying to, they're just kind of looking, I don't know what they're looking at, but they're just kind of guessing at what this r is. The r is based on the radius of the ribbon. So we're going to draw a ribbon. Okay, we're going to draw a ribbon. Drawing the ribbon is always based on your axis of rotation, not your independent variable. So whether we have x as the independent variable or y as the independent variable, doesn't matter. What matters is that we rotate it around the x-axis. So if we have, say, a typical interval here. Here's a delta y interval. So in a delta y interval, the ds is going to be the tangent segment starting from there. So it's going to be like this. It's a tangent segment, right? The tangent segment to the curve starting at the beginning of the interval. But now that thing is going to be rotated according to the rotation to generate the surface. It's not going to be rotated around y. You see that that ribbon will not be on our surface. So it's going to be around x. Draw the typical ribbon. Draw the typical ribbon. This is what's going to help you get R right. Right, there's our ds. Okay. So this is, now, so notice that little ds came from a delta y interval, but then because we got the surface by rotating around the x-axis, the frustum of the ribbon is rotated around the x-axis. Okay, does that make sense? Super important. So what's the radius? The radius is now, we're going to ask that same question again. Is it an x value, a y value, a big variation in x, or a big variation in y? The radius of that ribbon.
Y value.
She wants y value. Agree? Yes, right? Distance from the x-axis. So from here up to here, that's the y value. That's the radius of my ribbon. Okay, so our rate of change of surface area is going to be what? 2 pi, what is the radius? Y. Square root of 1 plus g prime of y squared. Do I have to change this now? What's my independent variable?
Y. So
Independent variable is y. So I'm done. It is y, right? So the radius is just the value of y. As y increases through these intervals, generating ribbons, the value of the radius is just the y value. I'm done. I don't have to change this into x because I want it in terms of y. And it is y. Does it make sense? So let's see, does that agree with what we said? So now I got the rate of change of big S for the g function, right? So the rate of change of big S for the g function is 2 pi y, 1 plus the rate of change of y squared.
So this is why it would be helpful to graph the original function with y as the independent variable.
No, yeah, it would say in this case, I guess it saved you one step. It saves you one step, but that's not why we're doing it. That's not why I put y as the independent variable. So I put y as the independent variable just to practice our conception of graphs and functions. So, and it turns out then, having done that, now I don't have to change, because y is the independent variable and radius is y, I don't have to change that. Okay, so let's graph our, so then our surface area function will be capital S, again, y is the independent variable, at my rate function that I just defined there. So questions on, there's the rate function, 2 pi y times my square root. So then I can use that to define surface area. And again, I want to put the surface area function over here with y values here and my surface area on the y-axis. How do I do that? So what do I want my y-axis to be over here? Do I want it to be the independent variable y or values of surface area up here? So
we want it to be surface area.
Surface area.
And then the y.
right, so I want this is values of surface area using the function notation, right? So I want to put on my y-axis over here values of surface area over here. And so what should my arguments be? Starting value of y equals 1. And then as a function of, I want it to put it on the horizontal axis, right? I want to put my independent variable here on the horizontal axis over here. So I'm going to put here x prime, and then graph that to 4. And then, so what's this going to look like? It's going to start at 1, and it's going to go up. And it's going to go up a lot more because surface area is a lot bigger quantity than just walking along that curve, right? It's like all this area on the side. So let's change the graph a little bit. Zoom out on the y-axis. And so how can I get the total surface area of the bell? I want to use my graph to get the total surface area of the bell.
Very end value of the blue graph.
That's right. So I'm going to come here to x equals 4 on the right graph. When x equals 4 on the right graph, it's telling me my total surface area of that bell shape or that funnel shape, 51.18. What does this x equals 4 mean? It means that I've gone 4 in the y direction, 4 up here to the y value of 4 in this graph. And when I reach y equals 4, the amount of surface area that I've created is 51.1814. Okay, questions? So,
This is what our homework is on due on Wednesday, right?
yes, you have some homework on this due Wednesday. So Wednesday morning, there's actually two iMath AS homeworks due Wednesday at 9.
Okay.
The first one's short, second one's a little longer.
Thanks.
Yep. Okay, so remember, to figure out these radius, lots of practice figuring out what the radius is. Draw a picture of the typical ribbon. That's what will get you the right radius. It's not, so it might be the independent variable, it might be the other variable. Okay, it might be a big variation in the independent variable. It might be a big variation in the other variable. So that's why draw a picture according to your setup to get that radius right. Okay, I wanted to finish up a little bit that we didn't get a chance to finish at the end of class today on Monday. And there was one more kind of problem to this that I wanted to talk about. So we found the rate of change for the surface area, right? We took this red curve, we rotated it around the x-axis to make this kind of funnel or bell shape. And we said that we're going to let y increase through delta y intervals. We took in a typical interval, we took the ds segment, which is what tangent to the curve starting at the beginning of the interval. We rotated that around the x-axis to form our frustum or ribbon. And then we said that the key component we need for the rate of change of surface area was the radius. And so we said that radius was the y-coordinate, right? It was the distance up from the x-axis out to the edge of the ribbon, rotating around the x-axis. Therefore, that radius was y. Since our independent variable was also y, we were done. It was just 2 pi y times the square root expression that we got from the arc length rate of change. So we wrote that rate of change function. We wrote the accumulation function of surface area, right? So as y increases through delta y intervals, we're generating this frustrums, and those frustrums kind of get generated kind of from left to right as y increases. And then, so we could represent the total area of the surface as the surface area function 1, 4. They give us 51, and I think we already saw that in the graph. If I come to the graph here, this is my graph of what y coordinate on the left graph versus surface area generated by the rotation. So, and there we saw at 4, the rate of change was 51.1814. So this is a y coordinate of 4 gives a accumulation of surface area of 51.1814 for the whole funnel or the whole bell. Okay, so the next activity, that's kind of review. So the next activity was that. So we redefined the curve of G, same curve of G, but as a function of x named f. So what we have was, so we're going to redo this problem, but now with the independent variable being x. So we had g of y equals ln of y. And we knew that this was our x coordinate, right? So x was ln of y. So we want to now rewrite this as as y equals some function of x. Well, that means we would have to solve this for y to get an expression of x. And I think someone said in class Solving this for y means what's the inverse function kind of natural log? Well, natural log is the inverse of e to the x. So these are equivalent, but the form is now our y equals function of x. So we're going to use a function of x as e to the x. So that's really what we were working on here. We were working on e to the x starting at 0. So now we have 0. And then what would our x-coordinate be here? Well, it's the x-coordinate we got when we put 4 into g. So g of 4 is ln of 4. So ln of 4 is the x-coordinate. So we're gonna consider f of x is e to the x from 0 now, right? Because this starting point was y equals 1, but it's x equals 0. 2 x equals natural log of 4, which is the x-coordinate corresponding to this y-coordinate of 4. So exact same problem written in terms, a function in terms of x. So there it is, f of x equals e to the x. So we're still going to rotate the curve about the x-axis. We're still going to rotate the curve about the x-axis. Just now, we're going to generate the frustums as x increases through. I can use a different color here. Something red. As x varies through delta x intervals. Okay, so for a typical interval, say this one, come up here, we're going to draw the same ds, right? The same ds is going to be tangent to the curve at the starting point of the interval. We're going to take that ds, and since it's the same surface as before, resulting in rotating around the x-axis, that ds is also still going to be rotated around the x-axis, so we have the exact same frustum, or same ribbon. So it's the same ribbon whether x is our independent variable or y is our independent variable, because what determines the ribbon is the axis of rotation, which hasn't changed. We have the same axis of rotation, same surface we're generating. So it's just how we get to those intervals now is through x intervals rather than y intervals. But we get the same ds, and then now that same ds is rotated around the x-axis. Okay, so our rate of change of s, now according to function f, not g, is going to be a function of x now, not y, right? So now x is our independent variable, and so we know it's going to be 2 pi times the radius. What is the radius of our frustums, or radius of our ribbons? Well, it's the same ribbons as before, so it's still 2 pi y. And we'll have 1 plus. Now we're using our f, which is a function of x. So it's going to be this. Now we ask the question, do we need to rewrite this in terms of our independent variable? Now the question is yes. Now our independent variable is x. We have y here. Okay? The radius is still y, but now we just have to rewrite it in terms of x. So what is y in terms of x? Y is e to the x. So if we want, we could even put the derivative of f of x in here. Derivative of f of x is e to the x. So I'm going to leave it as derivative so that's not confusing, because if I write e to the x, then you might think it's just f, but it is f prime. Okay, so we got the rate of change function. So let's, I think I already have that entered in here. Let's see if that agrees. 2 pi f of x, right? F of x is our e to the x, which I defined right here. And then 1 plus e to the x squared. So I think, I wrote this in a previous semester. I think I prefer the other way around. I think I prefer having this be e to the x and this be f prime. So you can really see what's going on here. This is our y coordinate rewritten in terms of x. And this is now our function f's derivative squared. Now, I didn't change anything. I just changed the notation, the form, right? Both, the way it was originally was correct. It was correct because e to the x is f of x, and f prime of x is e to the x. Okay, so I think I prefer writing e to the x here to show that it's y is a function of x, and then keeping it f prime there so we know that we're actually taking the derivative under that square root. Okay, surface area function, then we've got the rate of change, so we can write the surface area function. So there's that. And so now I want to graph the surface area function in the right-hand pane. So let's turn off, we got this was for the independent variable being y. Let's turn off the arc length function. Don't need that anymore. We're just talking about surface area now, so I'm going to turn that off. So we're going to graph the surface area function in the right-hand pane. And how do we do that? So we know we're going to use x prime and y prime to indicate we want it over here on the right. And so what do we want to put on the vertical axis? So we want to put surface area just like we did before. So our y prime is going to equal surface area, this function. And now what do we want to put on the horizontal axis? Well, now it's kind of like we're back to what we're used to. We're back to our normal conventions. We want to use our x, our independent variable for this new approach to this problem was x. So I'm just going to transfer the independent variable x over here is still going to be the independent variable x over here. It's just now y values on this graph will be the surface area. So I'm just going to, and now we're going to start at, for letting x increase through delta x intervals, my curve starts at x equals 0, right? Start at y equals 1 and x equals 0. So now it's 0. And then on the x-axis over here, I want to put this variable, which was my independent, or x, in the accumulation function. All right, and we're going to graph that from 0 to, and then to natural log of 4. Let's take a look at that. So let's change up the color here. How about purple? All right, so here was our, let's make sense of this here. So first let's interpret a point on the graph. Let's get this point right here. So that's the point, let's do this point here instead. X equals 0.6875 and 11.2153. And what does that point mean? So what does this point on this graph mean? It means that when my x value over here is 0.6875, right, so again, x is increasing through delta x intervals here, generating frustums that are these ribbons, and accumulating surface area as the ribbons grow grow in 2 pi r, right? So the 2 pi r is adding on surface according to ds. So when x reaches 0.6875, the amount of surface area that's been generated thus far, and so let's actually draw that. Got my fancy multicolors here. Okay, so at 0.6875, which is about here, you draw it like this, So when x has reached 0.6875, we've generated how much surface area thus far, right? How much? 11.2153. So I'll do that in nice light green. So up until x equals 0.685, we've generated 11.2153 units of surface area of the whole funnel or the whole bell. Okay, so are these right? So what's going on here? So x varies from 0 to ln of 4. And while that happens, y could vary from 1 up to 4. So we're seeing that. So x varies from 0 to natural log of 4. Y varies from 1 to 4. So how do we see the total surface area of the bell in this graph? Well, that occurs when x reaches natural log of 4. When we reach here, then we've accumulated all the surface area on that bell, and so we should get the same value that we got before. So if I come over here and I grab this, I'm gonna come up to ln of 4, which is the end of my curve right there. That's my ln of 4 value, and at ln of 4, lo and behold, the y value on this graph tells me the total surface area of the bell, which is the same as before. Which is the same as what? The surface area when we reached 4, y equals 4, originally, when we did it the other way. So you get the same surface area, 51.1814, when you get to the end of your domain for x, ln of 4, versus when you get to the end of the range or the end of the domain on y, which is 4. So both give you the same surface area. So S sub f of 0, ln of 4 equals S sub g of 1, 4 equals the 51.1814. And so I can just confirm that with our function here. S f of 0, ln of 4, 51.1814. So the same as S g of 1, 4. Look at that. So as y varies from 1 to 4, we get the whole bell. And that's also the same as x varies from 0 to ln of 4, we get the whole bell. And so we get the same amount of surface area in both cases. Okay, so in recitation on Tuesday, you'll get more examples of this stuff. And to help you with the homework, please get the support you need, whether that's office hours or you can email us questions. Okay, see you Wednesday.